All right. Hope everybody had a good weekend. We have a short week coming up because you don't come to school on Friday. Just make sure everybody knows, huh? It's Good Friday, so you get a 3-day weekend. Easter Sunday is less than a week away now. A couple things going to be happening this week. When you walked in today, you picked up the homework assignment for our current lesson. We should be able to wrap that up by tomorrow. Okay, I don't see any problems. So that's going to be due on Wednesday. I'll go ahead, we'll turn that in, talk about it on Wednesday, turn that back to you on Thursday because you have your test, and you can always use your notes on your tests. The test is all multiple choice except for one problem, and it's going to cover vectors. Hello. Hey. Okay, Lexi. Okay. All right, yes, ma'am. Counselors. There you go. Okay, tomorrow I have a little exit ticket for you. It'll help you practice, some of the concepts that we start going over today. But I think that's pretty much it, unless anybody has any questions.
Do I go right now?
Yes, ma'am. Okay. Well, let's see. We were talking about, since last week, dot products. And then we went through a couple of other things. We did some expressions here. We found out how to tell if the angle between two vectors was going to be acute, orthogonal, or obtuse, and I'll remind you what that means in just a second. And then we were currently on actually finding the angle between two vectors. We're using this formula right here. Okay, so we take the dot product. That means to multiply. What were the double bars around my vector again? I always forget that. That was the magnitude. That was the square root of a squared plus b squared. Okay, so I remember the last time we actually had a lesson on Thursday, because I think Friday the quiz actually took all the period. We got A done, but we didn't get B done. So let's see. I want to find the angle between W, whose component form is 5 square root of 2, and vector Z, whose component form is square root of 2 and 2. Okay. Well, let's see here. Here's my formula. Cosine inverse of the dot product over the product of the magnitudes. Well, let's start with the dot product, how I multiply two vectors together. So I'm going to take 5 square root of 2 times square root of 2, 2. How do I multiply vectors again? I forgot how to do that. Okay, there we go. So we multiply the corresponding values. So A times A, and we'll multiply B times B. All right, so 5 times the square root of 2, well, that's just going to be 5 square root of 2. Square root of 2 times 2, well, that's just 2 square root of 2. And then what do I do with those two products? You add them up. So here, they both have the same radical. So just think of it as, a variable. If I had 5x plus 2x, you would tell me 7x. So 5 square root of 2 plus 2 square root of 2 is 7 square root of 2. Okay, so I've got the numerator. Now I want to find the magnitude for both the vectors. Okay, so the magnitude of u. Now remember, the formula was the square root of a squared plus b squared. So this was going to be the square root of, a is 5, so that's going to be 5 squared, plus square root of 2 squared. Okay, so let me lengthen this a little more. So 5 squared is what? 25. But what happens when you square a square root? Yeah, they cancel out, so it's just going to leave me 2. Okay. So it looks like I have the square root of what? 27. Now, this is the one time, yes, ma'am. You can. Now, we can. This is an example when we can simplify because 9 times 3 will give me 27, and 9 is a perfect square. But this is probably the one time when we're trying to find theta in this formula. We don't have to worry about it. Just let the calculator carry that load for us. Okay, so right now I'm just going to leave that as is. But if we want to, we could. It'd be very easy. Let's do the same thing for v. The magnitude of v, so the square root of a squared plus b squared. So here's a, here's b. So once again, we have a square root of 2 squared plus 2 squared. Okay. Well, we just saw in the previous step that the square root of 2 squared is just 2, plus 2 squared is 4. So it looks like this one's what? square root of 6. So I have everything I need to go ahead and find the angle between these two vectors. All right, I've got the dot product and the magnitude of each. So now I just plug it right into that formula. So let's see here. The cosine inverse of, well, the dot product, we found that to be, what was that? 7 square root of 2 over the magnitude of u, we found that to be the square root of 27. And I'm going to multiply that by the magnitude of v, the square root of 6. See, I don't even need to multiply square root of 27 times square root of 6, figure out what that is. I'm just going to let the calculator give me the answer. Okay, so that's going to give me theta. So let's see here. What do we got? Cosine inverse. Ooh, going through the motion again. So control divide. So I'm going to go ahead and put 7 square root of 2. And then down here we had the square root of, I believe it was 27. Get out of there times the square root of 6. Okay. So just plug it in. Have no idea what this fraction will give me. But when I push enter, I'm looking at about 38.9 degrees. So I'd say you could probably make an argument for what? 39 degrees. Okay. So this is about 39 degrees. So let's take a look at this visually here. Or, well, no, I'm okay. Let's not worry about that. So if I were to go ahead and graph them, the angle between those, if they're both in standard position, we can go ahead and say it's 39 degrees. Okay. All right, good. Good. Any questions on that? No? Easy? Okay. You'll have a question like that on your test. Okay. Remember, I want to say the vast majority of it's multiple choice. I think I put one on there that was open-ended. Okay. Now, definition of orthogonal vectors. Okay, now orthogonal is a special word that we like to use when dealing with vectors. This tells me if two vectors form a right angle. Okay. That just means they're perpendicular. That capital upside down T is the symbol we use for that. So they form a 90-degree angle. Well, how do we know if they're orthogonal or perpendicular? If the dot product is what? If the dot product is 0. Okay. And remember from your chart earlier in the lesson, if I multiply two vectors, if I get a positive number, then we know the angle between them is acute. If I multiply two numbers and I get a negative, I know that the angle between them is obtuse. Okay. All right, so what we're looking for, hopefully, is going to give me a 0. Well, this one says, okay, we got two vectors. U is equal to 4, 6, and V is equal to negative 2k. It says find the value of k so that the vectors U and V are orthogonal. Well, let's see here. If it's going to be orthogonal, meaning if these are going to be creating a right angle between them, when I multiply them, it has to equal what? It has to equal 0. Okay, so let's set that up. Let's say 4, 6 times negative 2k. If I multiply these two, it should be 0. So we're wanting to find the value of k that's going to make this true. Okay, so how do I multiply vectors again? It's been a long weekend. There you go. Lilybell's absolutely right. We multiply the a's, we multiply the b's, and then we add them up. So let's see. What's 4 times negative 2? Negative 8. 6 times k, that's 6k. Add them up, and we should get 0. So see, now, by using the definition of dot product, how to multiply vectors, well, we gave ourselves a little two-step equation. Let me write this up here so I have a little more time, or room, I should say. Negative 8 plus 6k is equal to 0. What would I do first? Add the 8 plus 8 plus 8. There we go. So 6k is equal to 8. Divide through by 6. So what is 8 sixths? 4/3. There we go. That would be the value of k, so that if I multiply those, I would definitely get orthogonal vectors. Okay. What does orthogonal mean again? It means they form a 90-degree angle. That's exactly right. And see, it's right. Right. All right. Questions. Easy, right? Okay. No problems? Okay. Well, let's go ahead and start looking at how we go ahead and use some of these in the real world. We're going to have two types in this section. We're going to have incline problems. So problems where you got some item sitting on a hill or a slope, and you want to figure out what's the magnitude, the amount of force needed to keep it from rolling down the hill. And then we're also going to have work problems. Okay. Now, this right here makes it look horribly complicated. I'm going to go ahead and teach you, if you have an incline problem, there's a simple way to solve these. All you're going to do is use right triangle trigonometry. Okay? So let me show you how. Let's say we have a horizontal line here. And let's say this represents the incline that we're talking about. Okay, could be a slide, could be a hill, could be a ramp, whatever. But each of them is going to have some measure of incline. You're always going to be told, it's inclined 30 degrees or it's inclined 45 degrees or whatever. Okay, so let's say you have an object sitting on that hill. Okay, and that object could be anything. I mean, in a lot of these problems, we might be talking about a car or something along those lines. Well, we have a vector that represents a force due to gravity. Okay, so this object here is going to be pushing straight down, right? Okay. Well, you remember the other day or the other week when we talked about rewriting a vector in terms of its component forms? Okay. Those two vectors that would create a right triangle? Well, that's exactly what we're doing here. See, whatever this object on the hill is, it's wanting to go down the hill with a certain amount of force. So there's a vector that represents that. But there's also a vector that's perpendicular to the hill itself. Now, I'm kind of foreshadowing what we're going to do, but this vector that goes down the hill, we call that W1. The perpendicular vector, we call that W2. Okay. Well, the reason I'm drawing the diagram in this way, and you'll notice I'm trying to make it much less easier than the diagram they have there in your notes. Whatever angle you're provided right here, this angle theta is always going to be the same as that angle right there. Okay. So you'll notice I've created for myself using component form a right triangle. Okay, and this diagram is going to make it super easy to solve these word problems. Much faster than the word problems we were looking at last week where we were finding the resultant. Okay, so let's take a look at a problem. Let me see what you think. Okay. It says if the car in the diagram above weighs 2,800 pounds, it's on an incline of 15 degrees, what force is required to keep the car from rolling down the hill? So we're going to kind of flirt with physics a little bit. This isn't a physics class, so there's a lot of things we're going to be ignoring, like friction, things of that nature. We're just going to be looking at it pretty simply. Okay, so let me draw a diagram. Okay. Now I know that this is a hill problem because it'll say, it's on a hill or it's on an incline, something like that. So I'm always going to start by drawing that diagram that I just showed you. I can do better on a straight line. There we go. So let's say this is the hill right here, and we've got the car. Let's see if I can draw a decent car here. There you go. Not the world's best car, but that auto do it. Auto. There you go. Okay. So I know that this car is going to push down with a force of gravity by the amount that it weighs. So how much does the car weigh? 2,800 pounds. So I know that this one right here is 2,800 pounds. Well, remember, I can take that force vector and I can rewrite it using two other vectors, the components. Okay? Remember, the vector that represents the amount of force of the car wanting to go down the hill, remember that was W1. The perpendicular vector, that was W2. Well, the only other thing I need, what's the measure of incline here? It's 15 degrees. So I know that this incline is 15 degrees with the horizontal, but this is going to happen every single time. Whatever this measure is right here, this measure is going to be exactly the same. Okay. It's always going to be exactly the same measure. Now, let's think about this. We're trying to figure out the amount of force it's going to take to keep the car on the hill. We don't want it to slide down the hill. Okay. Well, what's going to happen if I were to match the amount of force that the car is wanting to go down the hill with. Whatever force it's wanting to go down the hill, what if I took that same amount of force and just went the opposite direction? What's going to happen to those two opposing forces?
Wouldn't it be constant? Wouldn't one force have to be greater than the other?
Oh no, actually if one was greater than the other, like for example, if the force going up the hill was greater than going down, what would the car actually be doing? Okay, it would be going up the hill, right? But we want the car to stay exactly where it is. So what's going to happen if I have two forces of the exact same measure? They're going to cancel each other out, right? Okay. Well, let's think about this. What we're trying to find is the amount of force that the car is wanting to roll down the hill with. If I know how much force the car is wanting to go down the hill, if I go ahead and apply that force opposite the car, those two forces are going to cancel each other out. That's going to be what's necessary to keep the car exactly where it is. Okay, so let me see if I can elaborate a little better. This triangle that we have right here, let me go ahead and recreate it over here. Okay, so remember the hypotenuse was 2,800 pounds, right? Okay, we know that this angle was 15 degrees, and what we're trying to find is this magnitude right there, what we call W1. So I want this side length. Well, think about it. It's just right triangle trig. Remember, that's represented by W1. What trig function can I use if I know a side opposite and a hypotenuse to the measure I have? Sine. I can say that sine of 15 degrees is equal to W1 over 2,800. How about I solve this? Multiply through by 2,800. There you go. Okay, so when those cancel, all right, we're going to have what we need. 2,800 times sine of 15. So I'm going to come on over here. Hopefully this will let me do this. Let me go back real fast. Okay, so 2,800 sine of 15. Okay. So what I found here was that the car is wanting to roll down the hill with 724.7 pounds of force. I know it's pounds because that's what the car weighs. That's the measurement I was given. So if I want to stop the car so it doesn't roll down the hill, I have to oppose that force with the exact same amount to keep it in one place. So what force is going to keep the car where it is? Well, that's just the answer we got here, 724.6. 724.6 pounds. That's it. Okay. If you have two vectors going at each other that have the exact same magnitude, they're going to cancel each other out. Okay. What do we think? Hey. Uh-huh. Uh-huh. That one's okay. You can go ahead and say 0.0 or just round it to the nearest whole number. That's fine. Yeah. Okay. All right. So let's try another one of these. Okay. This is, it's on the page that has the diagram with the car right about the middle. Okay. Okay, now there was a sheet that I passed out on Friday that I was hoping to get to that we didn't. It's going to look like this. Okay. It says vector projection, real world problems. Okay. All right, so I've got a couple more problems just like this. We're talking about an incline problem. Okay. Yes, that one right there. Exactly. And if you've lost it or misplaced it, or if you weren't here, I've got some right over there in the files behind Christian. Okay. So let's do another one of these together. Okay. This one says a 3,000-pound car sits on a hill, inclined at 30 degrees as shown. Ignoring the force of friction, what force is required to keep the car from rolling down the hill? Now again, they're showing the diagram similar to the packet I gave you. They're creating this based on a parallelogram. I don't think it's necessary to make the diagram that difficult. Start with a straight line. Draw your incline. Okay. And instead of drawing the car again, let's just say this dot right here. Let's say that represents the car. Okay. So the weight of the car is going to create a vector that goes straight down. That's my force vector. Okay. So what's the magnitude of that? Oh, yes, please. How much does a car weigh? 3,000. So I'm going to go ahead and put 3,000 pounds right here. Okay. Now, what I'm going to do is take this vector that's going straight down, and I'm going to create a right triangle using its component vectors. So I'm going to have a vector that's going down the hill, and then I'm going to have a vector that's perpendicular to the hill. Okay. The one going down the hill, we always call that W1. The one perpendicular, we always call that W2. Okay. Well, what's the incline of the hill? It's 30 degrees. So I'm going to go ahead and put 30 degrees right here. But remember, in this diagram, this bottom angle right here is always going to be the same measure. Okay. So if I want to know how many pounds of force is going to keep the car right where it is on the hill, all I need to do is find the magnitude of W1, just like I did a moment ago. So we're just going to use right triangle trig. Okay. In fact, what trig function did we use? Sine. Okay. So we have 30 degrees. So I'm going to go ahead and say sine of 30 equals, well, what would the ratio be? W1, because we're trying to find that parallel vector, W1 over 3,000. There you go. Every one of these problems is going to be solved the same way. That's all there is to it. In fact, now I'll go ahead and multiply through by 3,000. Okay, those are going to cancel. So how many pounds of force will it take to keep the car where it is? Well, it's whatever 3,000 times sine of 30 is. In fact, can anybody help me out? 3,000 times sine of 30. 1,500. 1,500 pounds of force. Does anybody want me to type it in the calculator?
No, we believe you.
You believe me? Okay. Pretty trustworthy. There you go. There was a little bit of hesitation there, but okay, I'll take it. Okay. But that's it. That's all there is to it. Okay. All right. Well, let's go ahead and try one more. But let's try one on our own. Now, this one says Mary sits on a sled on the side of a hill inclined at 60 degrees. What force is required to keep the sled from sliding down the hill if the weight of Mary in the sled is 125 pounds? See, it does not matter what the object is. It's always the same scenario. Yes, ma'am.
Are you ever going to make us give us two objects?
Oh, no. Like in this case, you got Mary sitting on a sled, which is on a hill. So all we're looking at is their combined weight. Okay. So let's start with the diagram. Always start with the horizontal line. Draw my incline. So in this case, it's a hill. I typically just go ahead and draw a dot to represent whatever it is here. So here we got Mary sitting on a sled. Okay. So the first thing I'm going to draw is the force vector that goes straight down. How am I going to label that? Okay. Because Mary and the sled weigh 125 pounds. So that's the amount that we're pushing down. Okay. Now I want to go ahead and rewrite this vector using its component form. Okay. So I've got a vector that goes down the hill, parallel to the hill, and then I've got another vector that's always perpendicular to the hill. The parallel vector is always W1. The perpendicular one is always W2. Okay. Yes, now that's probably going to be tomorrow when we find it. But there's a very simple way to find him as well. Okay. And in fact, what's my incline? 60. So if I put 60 here, where else can I put 60? Right there, that tiny little angle right here where it touches the horizontal. Yes. Uh-huh. You could, yes, actually, absolutely. Now, I'm going to be showing you a different way tomorrow called a vector projection. So we're going to be, it sounds worse than it really is. We're going to be doing a little bit of algebra to figure that out, but it's not bad. Okay. So in fact, what expression or equation can I create based on this? Okay, sine of what? So sine of 60 equals W1 over 125. And then Marcus says multiply by 125. There you go. That's it. So let's see what that is. It was 125 times the sine. Was it 60? There you go. So I'd probably say 108.3. There you go. That's how you work the incline problems. Okay, you pull your very simple right triangle equation right off the diagram. Okay, really all you need to know is how much the object on the hill weighs and what the amount of incline is. Every one of those problems is going to be worked the same way. Okay. Nope, not a lot. Okay. Easy, right? Okay, easy. Okay, well, let me go ahead and show you the other type of word problem that we have on this lesson. So if I'll go back to the packet over here. All right. Yes. So this one here, let's go to example 5. Now, these are work problems. Okay, so you're going to be able to tell the difference between, the incline or hill problems and the work problems pretty easy, just because, the way that it's stated. So here, we're going to find work by taking the dot product of two vectors, and you're always going to be provided two vectors here. Okay, one's the force vector, and then the other one, I always go ahead and refer to it as the distance vector. Okay, I always use the abbreviation AB because let's say you're sliding a container across the floor. Well, you're sliding it horizontally, right? So let's say here's the floor, here's the horizontal, and you've got, some container. Well, one part of it I'm going to go ahead and label A, and when I slide it along, I'm moving it a certain distance so that by the time I finish, point A is now at point B. Okay, I'm just sliding it across the floor. Okay. Well, what we're trying to figure out is how much work am I actually doing by sliding the object across the floor. Okay. Now, it's really simple to take care of. For the force vector, you're going to have to use a formula that we've been using since last week. Okay. The magnitude times cosine theta, magnitude times the sine of theta. Now, you're not going to have to typically do that with the distance vector. If you're pushing it on the horizontal, you won't have to worry about it. Now, if you're pushing it up like a ramp, you want to use that formula, but I'll show you that coming up. So let's see what the problem says. A large storage container is pulled 25 feet across a warehouse floor by a pulley system using a force of 80 pounds. The direction of the force is 55 degrees above the horizontal. Find the work done. Okay. Now remember, there's two vectors that we're going to be looking at. Okay. One's the amount of force that it takes to actually move the object across the floor, and the other one is the distance that you're moving it. Okay. Well, how much force is being used to pull the container across the floor? So what number would represent the magnitude of the force? 80. We're using 80 pounds of force. Now, does it tell me theta? Yes, 55, so I know that's theta. So I'm going to say 80 cosine of 55. What do you think the second part here is going to be? 80 sine of 55. Okay. All right. Now, for the distance vector, if it's simply going along the floor, you could use the formula if you wanted to, but you don't have to. Well, let's think about it. It's being pulled how many feet? 25 feet. So if it's being pulled along the floor, well, what's the angle of elevation? 0. There isn't one. Okay. So I could just say that the distance vector is 25, 0. Okay. I'm just pulling it 25 feet. Does anybody want me to go ahead and actually plug in the formula to show you that Even if you use cosine and sine, you're still going to get 25, 0?
Yeah.
We're okay with that? All right. So now, once you have these two vectors, in order to find the amount of work, all you have to do is take the dot product of the two. Now remember, what happens when I multiply two vectors? Do I get a vector or a scalar? Remember, I get a scalar. So I should be getting a number. That's the answer I'm looking for. Okay. Well, it's just like we did before. I'm going to multiply the corresponding parts. Okay. So I'm going to go ahead and say this is 80 cosine of 55 times 25 plus, okay, 80 sine of 55 times what? 0. But if you're multiplying anything by 0, well, that guy's just going to disappear, right? So all I got to do is figure out, okay, what's 80 cosine of 55 times 25? So 80 cosine, was it 55? Okay, get out of that times 25. So I'd say about 1,147.2 foot-pounds, okay, of force. Foot-pounds, yeah. Just because of the measurements we were given. We don't know the number of newtons. I mean, you could convert it if you want to. I'm not interested in doing that. Typically, we do things in newtons and joules, but since this problem was given to me in feet and pounds, we would actually just say foot-pounds. Have you ever heard that before?
I heard it like the little dude.
Little newts?
Yeah.
Like a little salamander?
Yeah. That's supposed to look
No.
It's like, look at it. Like a little lizard. How do you go back to the rock?
Yeah. So 1147.2. Foot-pounds. That's it. Okay. So if it's a work problem, all you have to do is multiply your force vector by the distance vector. Okay. Okay. Yeah, what's this? Oh, no, he's a gecko, right? Yeah, he's a gecko, yeah. Yeah, Geico. No, I know what you're saying, yeah. But what's the phrase that goes with it? 15 minutes could save you, what is it? Could save you 50% or more? Okay.
Hey, Mr. West.
So 15 minutes of math could save you 15% or more on car insurance? What?
The Paris Notre Dame Cathedral's on fire.
It is?
Yeah, that's what they sent out like a message on my phone.
What started it? Did they say anything?
No, all they say is like, yeah, it's on fire.
Oh, wow. Well, I hope they get it under control. It's crazy. The City of Lights. Okay. So let's go ahead and try another one. Okay. Now this one's actually given to me in newtons, so I know my answer is in joules. Yes.
On our homework that you gave us, we can actually find
Yes, but I'm showing you that tomorrow. Yes. Okay. In fact, those problems on your homework, they're not word problems. It's just straight formula. That's really the only thing left I have to show you in this lesson. Okay. So let's do this work problem. It says a person pushes a car with a constant force of 120 newtons at a constant angle of 45 degrees as shown. Find the work done in joules moving the car 10 meters. Okay, now, the key word you're looking for here is work. Okay, so every time you're looking for work, you're going to multiply the force vector times the distance vector. Okay, now the distance vector should be the easier of the two to find. In fact, let's just go ahead and write them out. How far is this guy pushing the car? 10 meters. So what would you expect his component form to be? Oh, not 10U, 10, 0. Because remember, he's just pushing it on the ground, right? I think you said U, yeah. That's okay. Like in the last problem, we were pulling the object 25 feet across the floor, so we had 25, 0. So the distance vector, just imagine you're starting at the origin and you're moving to the right. Okay. So now the force vector is the only one that we need to go ahead and use that formula. So we're using 120 newtons of force at what angle? 45 degrees. So 120 cosine of 45, comma what? 120 sine of 45 degrees. Okay. Is everybody okay with how I'm setting it up? Okay. Now all you got to do is take a dot product of the two, just multiply it. So I'm going to multiply 10 times 120 cosine 45, and I'm going to add it to the product of 0 and 120 sine of 45. Okay, so 120 cosine of 45 times 10 plus 120 sine of 45 times 0. But that's why these problems are so nice if you're pushing something along the ground. The second part here, when you have 0, you don't have to worry about that. Okay, so let's see, what's 120 cosine of 45 times 10? 120 cosine is 0. Cosine of 45 times 10. Okay. I'm getting 848.5. Okay. 848.5. Was that 48? I forgot. 848.5. Okay. So 848.5 joules. There you go. So there we go. Those are the type of word problems that we would see in this lesson. Okay. We have the incline problems where you create that diagram. Every time it's the same way. And then the work problems, you simply multiply the force vector times the distance vector. Okay, how we doing? Great? Okay. All right. Well, then that, I would say, is where we're going to stop for today. The only thing I have left is to show you guys, okay, what is called vector projection. And again, it looks worse than it really is. It's very, very easy. Okay, it's just a formula. But we'll look at that tomorrow.